everyone, and good afternoon, everyone. And thank you for joining my talk today. So actually, first I would like to thank Iman for organizing this online seminar series, which I think is a great idea, given that we are all working from different places now. In my talk today, I actually plan to talk about a spectrum sensing technique that we use in cognitive radio networks, and that is called the Sphericity test. Since most of you are actually not from communications, I plan to first give you like a quick introduction to cognitive radio networks and tell you a little bit about this particular spectrum sensing technique. So it may sound quite specific, but in this work, we actually used some very interesting tools, very nice tools that I plan to talk about, and I hope that you will find them interesting. Yeah, so I did this work with a really nice group of collaborators. So I have Professor Peter Smith and Associate Professor Pavel Mahorski. They're from the Victoria University in Wellington in New Zealand. And I have Associate Professor Andrea from University of Bologna in Italy. And Professor Jamie Evans, of course, from our own department. Okay, so to start with, as wireless communications researchers, one of the major problems that we face today is we have this limited frequency spectrum, but there are more and more users coming into the network, but the frequency spectrum is limited. So we want to make sure that this limited frequency spectrum is not wasted. So we want to make sure that it is properly utilized. But the spectrum measurements actually indicate that nearly 70% of this licensed spectrum is underutilized at some places and some times. That means the licensed users, they do not use the spectrum all the time. So that is a waste of the frequency spectrum. And this cognitive radio is a technology that we can use to allow someone else to use the spectrum when the licensed users are actually not using it. So basically we have these primary users in the network, and they're licensed to use the spectrum. And we also have these secondary users, and they're unlicensed, but they are allowed to use the spectrum when these primary licensed users are not using the spectrum. So this is basically a method that allows these primary and secondary users to sort of coexist and share the spectrum. And that way we can increase the spectrum utilization. So for this whole thing to work, this whole cognitive radio network concept to work, these secondary users should be able to properly detect the presence of primary users. If not, if the secondary users start transmitting when these primary users are also transmitting, it will cause a lot of interference to our licensed users, and we don't want that to happen. So the secondary users should be able to properly detect that there is a primary user or not before it starts transmitting. So for that, we use this technique called the spectrum sensing. And what spectrum sensing does is, it is basically the secondary user's ability to sense the presence of the primary user. So it is basically based on the received signal, the secondary user make a decision about the presence and absence of primary users. So you can think of that as a detection problem, basically. So we can formulate this spectrum sensing as a detection problem, and you can formulate it as a binary hypothesis test. So basically the null hypothesis, this denotes the absence of primary users, and the non-null hypothesis denotes the presence of primary users. And in the past, researchers have done quite a lot of work in this spectrum sensing, using different spectrum sensing techniques. And in this work today, I'm going to talk about this Sphericity test, which is a really nice spectrum sensing technique that also performs quite well. And we did quite a lot of analysis based on this particular spectrum sensing technique. And I plan to talk to you a little bit about some performance measures that we derived, like the false alarm and detection probabilities, and also tell you a little bit about some other spectrum sensing techniques that we've derived based on this sphericity test called the multi-sample sphericity test and also the meta-analysis based sphericity test. So that is the outline of my talk. Okay, so to tell you about this sphericity test, I'm going to use a system model like this. Let's assume that we have P primary users in the network, and these are my licensed users. And I have M secondary user terminals. And these are my unlicensed users. And my goal is to actually decide whether there are primary users present in the network or not, based on what is received at these secondary user terminals. And I assume that each of these secondary users, they have different number of antennas. Like the secondary user 1 has Q1 antennas and so on. And let's say in total, I have K number of antennas. And all the signals that are received at these secondary user terminals, they have been sent to this fusion center. So this is a central processor that collects all the information received at these secondary user terminals, and we combine them all in here and process them globally to make a decision about the presence and absence of primary users. So basically, since I consider all of these signals to be sent up to this fusion center, I call this a centralized approach. Because later on in the seminar, I plan to also talk a little bit about some decentralized approaches. Okay, so I can write the signal received at the fusion center in this form. So if I assume that I collect signals over, say, n times samples, I have this n columns in this X matrix, and each of these columns are k by 1 vectors, because I have k antennas in total. So I have this k by n matrix, which is my received signal matrix. And if I look at the nth column of this matrix, I get something like this. So when there are no primary users present in the network, this nth column is simply noise, because when there are no primary users in the network, all I receive is simply noise. So this omega n is my noise vector. But under the null hypothesis, when there are primary users in the network, this omega n is actually, so apart from this noise vector, I also get this term, which corresponds to the signals that are transmitted by the primary users. So basically this H matrix, that is the channel matrix between the primary users and the secondary user terminals. It is a K by P matrix. And this Sn is the data vector. It is the data vector that was transmitted by these primary users. And I also get this noise vector. So this is what I receive when there are primary users in the network. So based on this received signal, based on this X matrix, now I want to make a decision about the presence and absence of primary users. And researchers have used different techniques. Like, for example, under the energy detection, we check the energy level of this received signal matrix. But under the sphericity test, what we do is we actually check the structure of this received signal matrix. And how we do that is like this. So first, based on this received signal matrix X, I calculate this R matrix, which is the sample covariance matrix. So it is simply XX dagger. So I calculate the sample covariance matrix. And when there are no primary users in the network, this R matrix is simply an uncorrelated, it has an uncorrelated complex Wishart distribution. So I can write the population covariance matrix, which is the expected value of this R matrix divided by N. So it is simply a diagonal matrix when there are no primary users in the network. But if there are primary users, then this has a correlated complex Wishart distribution because of the correlation created by these primary users. So when there are primary users in the network, the sigma matrix now is slightly different, because apart from this term, I also get this term that corresponds to the signals transmitted by the primary users. So basically, the structure of this population covariance matrix, it changes depending on whether there is a primary user or not. So that is what we check under the sphericity test. So you can basically reformulate your hypothesis testing for the sphericity test like this. So you declare the null hypothesis if your sigma matrix is equals to a diagonal matrix like this. So that is how we declare the null hypothesis. And if it departs from this diagonal structure, I declare the non-null hypothesis. So that is the hypothesis testing for the sphericity test. And this notation simply means that the difference between these two matrices, it is a positive definite matrix. Okay, so we have defined the detection problem. And next, we are going to come up with a test criteria that we can use to solve this detection problem. And for that, we used the generalized ratio, generalized likelihood ratio. So this is basically a ratio between likelihood functions, a ratio of likelihood functions. In the numerator here, I have the likelihood function of the observation matrix under the null hypothesis. So this is the likelihood function of this X matrix under the null hypothesis. And this is the likelihood function of this X matrix under the null hypothesis. So this defines my generalized likelihood ratio. And by maximizing these two likelihoods over the unknown parameters, I can come up with a test criterion like this. So this is basically my generalized likelihood ratio test statistic for the sphericity test. So under the sphericity test, what we are really doing is, based on the received signal, we calculate the value of this test statistic. We calculate the value of this test statistic. And if that is above a certain user-defined threshold, like in this case, it is zeta, it is a user-defined threshold. And if it is above this threshold, we declare the null hypothesis. And if it is below the threshold, we declare the non-null hypothesis. So the reason why we declare the null hypothesis when this is above the threshold is because in the numerator here, I have considered the likelihood function under the null hypothesis. So because of the way I've defined the likelihood ratio, when this is above the certain threshold, I declare the null hypothesis. And if I define it the other way around, this would be the other way around. So that is the test statistic that we use for the sphericity test. And based on this test statistic, we actually did quite a lot of analysis. And the first performance measure that we derived is the false alarm probability. So the false alarm probability is simply the probability that we wrongly say that there is a prime user. So it is basically the probability that this test statistic, that is the test statistic defined under the null hypothesis, is less than or equals to my user-defined threshold. Because when this is less than or equals to the threshold, I declare the non-null hypothesis. And if this is the test statistic defined under the null hypothesis, then this probability gives me the false alarm probability. So basically what I want to find is the CDF of this random variable in order to find the false alarm probability. So to do that, I will just give like the main steps of this derivation, just to give you an idea about the approach that we took. We actually used this reference textbook by T.W. Anderson. And in this textbook, he analyzes an asymptotic expansion of the distributions of the likelihood functions. And he uses, in order to use this theory of asymptotic expansions, we had to first find this nth moment of our test statistic. So here I have written the exact expression for the nth moment of the nth power of this test statistic, which I could write like this in terms of several gamma functions. So as you can see, these moments are certain functions of gamma functions. So once we present it in this form, we can, based on this general theory of asymptotic expansions, we can write the CDF of this random variable, which is the log of this test statistic, times a constant. We can write this, the CDF of this random variable, in terms of a summation of several chi-squared random variables. Actually, the exact CDF of this random variable has several terms that has higher order chi-squared random variables, but we ignored the higher order terms and then approximated this CDF by this probability, where this has a chi-squared random variable with f degrees of freedom, and f is given by this constant. So since what we want to find is the CDF of this random variable, based on this approximation and doing a simple change in variables, we can find the CDF of this random variable. And that is how we found the false alarm probability, which takes a form like this. So it was a really simple expression in terms of the chi-squared distribution, but it was an approximation. So just to give you an idea about how accurate this approximation is, I've included one numerical example here. Here in the y-axis, I have the false alarm probability. And in the x-axis, I have zeta, which is my user-defined threshold. And I have given the plots for several parameters, like I'm changing m, which is the number of secondary user terminals, and also n, which is the number of samples I collect. And I've set the number of antennas at the secondary user terminals to 2 in all of these cases. And as you can see that the simulation and the analytical results, analytical approximation, they're quite close, and it was quite an accurate approximation. Okay, so the next performance measure that we analyzed is the probability of detection. So the probability of detection is basically the probability that we correctly say that there is a primary user. So that is basically the probability that this test statistic, which is the test statistic defined under the non-null hypothesis, is less than or equals to my user-defined threshold. Because again, when it is less than or equals to the threshold, I declare the non-null hypothesis. So if this is the test statistic under the non-null hypothesis, then this probability gives me the detection probability. Since this random variable takes a completely different form, in order to find the CDF of this random variable, we had to use a slightly different approach. And what we did was, under the non-null hypothesis, first we actually noted that the log value of this random variable is closely Gaussian. So we were motivated to first approximate the CDF of this random variable using this a new random variable, let's say Z, which has a Gaussian distribution with a certain mean and a certain variance. But the question was, what was this mean and the variance? And to find these two values, we used an approach like this. So let's say, for example, I have a random variable t, of which the log value has a Gaussian distribution with a mean mu and a variance nu squared. And if I define another random variable, let's say x, if it is equals to log of 1 over t, this x2 has a Gaussian distribution with the same variance, but the mean is just minus mu. So this simply means that 1 over t is equals to the exponential of x, e to the power x. And if I write the first and the second moments of this random variable like this, the first moment and the second moment of that random variable, so that is basically the expected value of e to the power x and the expected value of e2x. And I can easily find these two because x has a Gaussian distribution, and these two simply can be found using the moment generating function of a Gaussian random variable. So it takes these two forms. So if I call this m1, which is the first moment of this random variable, and this is m2, which is the second moment of this random variable, and I take the log values of these two and write them in terms of mu squared and nu squared. And solving these two equations, I can find expressions for mu and nu squared just in terms of m1 and m2. So basically, in order for us to find mu and nu squared, all I need to find is m1 and m2. So that is basically the first and the second moments of this 1 over t random variable. So that is the approach that we took. So if you have a random variable of which the log value has a Gaussian distribution, you can find the mean and the variance of that Gaussian distribution by simply finding the first and the second moments of 1 over that random variable. So that is the approach that we took in deriving the probability of detection. We could find an approximation like this for the probability of detection, where the set is it has a Gaussian distribution like this. And again, this mu and nu squared can be written in terms of M1 and M2, where M1 and M2 takes this slightly complicated form. So here we have to find this M1 and M2 is the test statistic, the first and the second moments of 1 over this test statistic. Okay, so that is the distribution approximation that we found for the probability of detection. And again, I've included one numerical example just to give you an idea about the accuracy of this approximation. Here in the y-axis, I have the probability of detection. And again, in the x-axis, I have zeta. And I have just considered 3 realizations because every time I do a simulation, I have to generate my channel matrix, the H matrix, when we talk about the probability of detection. So these are 3 instances of that channel matrix that I have given here. Just to give you an idea about the cases, like this is one of the worst cases where we got a slight gap between the simulation and the analytical results, but overall it was a very accurate approximation. Okay, so that was in the first part of the talk, I was actually presenting this centralized approach in the sphericity test, because in the system model that I presented to you earlier, we assume that all the signals that we received here, they are being transmitted to this fusion center or to the central processor. So that was a centralized approach because we wanted to calculate this test statistic to make a decision about the presence and absence of primary users. But in order to calculate this test statistic, basically to calculate this determinant of the R matrix, I want all the information received at the second user terminals. So all the raw data needed to be sent up to the fusion center. But the problem is it actually creates a lot of network overhead. So what we did next was we looked at some decentralized approaches that reduces the amount of information that we sent up to the fusion center. So the basic idea was we allowed the second user terminals to do some processing based on what is received at the second user terminal. So here, based on what is received at the terminal, we do some local processing, and this processed data is then sent up to the fusion center. So not the raw data, but some processed data is sent up to the fusion center. And at the fusion center, we combine all of these processed data to make a decision about the presence and the absence of the primary users. And in this work, we actually came up with 2 decentralized sphericity test methods. The first one is called the multi-sample sphericity test, and the second one is the meta-analysis based sphericity test. So I will talk a little bit about these 2 next. Okay, so under this decentralized approach, we actually, so like I said before, we allowed the secondary user terminals to do some processing locally within the terminal. So now we can redefine our hypothesis testing under the decentralized approach like this. So we basically declare the null hypothesis if my sigma m, where the sigma m is the population covariance matrix at the secondary user terminal m. So before we had a sigma here, which is the population covariance matrix by collecting all the signals received from the secondary user terminals. So that was the big sigma that we calculate at the fusion center. But now we allow the secondary user terminals to do some processing. So we basically allow the secondary user terminals to calculate this population covariance matrix locally within the terminal. And if that is equals to this diagonal matrix for all the secondary user terminals, we declare the null hypothesis. So we say that there are no primary users. And if at least for one of them, if it departs from this diagonal structure, we declare the non-null hypothesis. So that is how we define the, for the decentralized sphericity test, that is how we define the hypothesis testing. And then we followed quite similar steps. First, we, just like before, in order to solve this detection problem and come up with the test criterion, we use the generalized likelihood ratio. So here in the numerator, I have the likelihood function of the observation matrices under the null hypothesis. And in the denominator, I have the likelihood function under the non-null hypothesis. And by maximizing these two likelihood functions over the unknown parameters, I can come up with a new test statistic that is for this decentralized approach, and we call this the multi-sample sphericity test. So by looking at this new test statistic, or new generalized likelihood ratio test statistic for the decentralized case, and comparing it with what we had before, we can now see that in order to calculate this new one, all we need is simply the determinants and the traces of these local sample covariance matrices, the determinants and the traces. So before, previously, in order to calculate this one, we actually needed all the raw data to be sent up to the fusion center. But now the idea is something like this. So basically, all the secondary user terminals, they calculate their sample covariance matrices locally and calculate the trace and the determinant. And that is all that we need at the fusion center to calculate this new test statistic, the multi-sample sphericity test. So instead of sending all the raw data up to the fusion center, all we have to send now is just two real numbers, and that significantly reduces the amount of network overhead. So based on these received signals, we calculate this new test statistic and check if that is above or below a certain user-defined threshold, and declare the null hypothesis or the non-null hypothesis. So that is the idea behind multi-sample sphericity test. Again, with this one, we actually did a lot of analysis, and we derived the false alarm and detection probabilities. We followed quite similar steps like we did with the centralized approach, and we could approximate the false alarm probability using a chi-squared random variable, and the detection probability, again, using a Gaussian random variable. So just to, again, since these were approximations, to give you an idea about the accuracy of these numerical results, I've included these numerical results. So here, in the first plot, I have the false alarm probability, and the second plot is the detection probability. In the first one, I have considered 3 scenarios by changing the number of antennas at the secondary user terminals to different values. And in here, I changed the number of samples that I collect from 50 to 100 to 200. So as you can see that in almost all the cases, the approximation and the numerical results, they actually fall almost on top of each other. So that was the first decentralized approach that we took. And then next, we actually considered another method where we reduced the amount of information that we sent up to the fusion center even further. And we used a tool called the Metaanalysis that can be used to combine tests from, combine results from multiple tests to come up with a global conclusion, or to produce like one conclusion. So it makes use of these extreme value probabilities, or they're commonly known as p-values. So we allow these, we let these secondary user terminals to calculate what is called the p-value and send it up to the fusion center. So what these p-values mean is, it is simply a measure that tells us how likely the null hypothesis is. So it is defined like this. it is actually the probability that the observed value of the test statistic is less than or equals to the test statistic, the random variable, under the null hypothesis. So if I explain it graphically, it is basically if this is the PDF, the probability density function of my test statistic under the null hypothesis, and if this is my observed value t bar, then this tail probability is my p-value. So the larger the p-value is, the more likely that the null hypothesis is true. So it is a measure that tells us how likely the null hypothesis is. And by taking p-values from different independent tests, we can combine them all using this tool called the meta-analysis to come to one global conclusion. And there are many methods that we can use to combine these p-values. And in this work, we use this Fisher's method, which is quite popular. And then we combine the p-values using this equation by taking the log of the p-values and then summing them up to produce one global test statistic. So basically the idea under meta-analysis is something like this. So at each cognitive radio, we calculate the p-values. So that is basically based on the signal that is received here. We calculate the test statistic based on the received signal. Say at the secondary user terminal, I calculate this TS1, and then I want to calculate the p-value based on this test statistic. And since the definition of the p-value is this, to calculate the p-value, actually what I need is the CDF of this test statistic evaluated at this value. So basically, since we already know that this CDF can be approximated using a chi-square distribution, I can actually approximate the p-value by using this chi-squared random variable that has F1 degrees of freedom. So at each of these secondary user terminals, based on this received signal value, I calculate the p-values and then send them up to the fusion center. And at the fusion center, I combine them all using this Fisher's method and check if that is above or below a certain threshold and declare the null hypothesis or the null hypothesis. So that is how this meta-analysis approach works. So in this way, we actually only send one real number up to the fusion center, whereas in the previous one, we sent two real numbers. Okay, so with this one, also we analyze the false alarm probability. We could actually calculate the exact expression for the false alarm probability, and it was quite straightforward because under the meta-analysis, this is what the test statistic is. And to calculate the false alarm probability, I want to find the CDF of this random variable. And so that means to find the CDF of this random variable, I want to find the CDF of this p-value, which can be found by using this inverse transform method, because the p-value is defined using this probability. And that basically means that it is the probability that this test statistic, which is the test statistic under the null hypothesis, evaluated at this value. So if I can write that as the CDF of this test statistic evaluated at this value, but I can easily, since this TSM bar has that is a continuous random variable, I can write that as it is actually the inverse CDF of this random variable u, where u is a uniformly distributed random variable between 0 and 1. And simply plugging that in here, I can say that my PM, the p-value, has a uniform distribution between 0 and 1. So since p has a uniform distribution, the log of p minus log p has an exponential distribution. And since I have a sum of m such terms, I can say that this random variable has a chi-square distribution with 2m degrees of freedom. So based on that, I can find the exact expression for the false alarm probability, which takes this form. We actually couldn't derive the expression for the probability of detection, but since this is an exact expression, I didn't include any numerical results in the talk today. Okay, so before concluding, I wanted to just sum up that in this talk, I presented these two methods that we analyzed in the past. And in these two methods, the first multi-sample sphericity test needed to send two real numbers up to the fusion center. And the meta-analysis is actually half the amount of information. So we said just one real number, and that real number is a p-value. So it is a probability value. It is a value between 0 and 1. And we also analyzed two other methods, which were quite simple. That is based on binary fusion. So basically, each second user terminal, based on the sphericity test, they make a decision about the presence and absence of primary users. So they make a binary decision. And then that binary decision is sent up to the fusion center. And that is combined based on the AND operator or the O operator. So that is the binary AND and O fusion. So in that way, we even further reduce the amount of information that we send. It's just one bit that we are sending up to the fusion center. So coming down, we actually kept reducing the amount of information that we send in the network. But the other question is how does these methods perform? So to give you an idea, I included one numerical example here. Here in this one, I have in the y-axis, I have the probability of detection, and in the x-axis, I have the false alarm probability. So like you know, the probability of detection is the probability that we correctly say that there is a primary user. So we want it to be as high as possible. And the false alarm probability is the probability that we wrongly say that there is a primary user. And we want it to be as low as possible. So we want our spectrum sensing technique to be operated here at this upper left corner. So as you can see, the multi-sample sphericity test, which is the blue line here, it outperforms all the other three methods, and then the meta-analysis and the binary O and binary N fusion. So as we reduce the amount of information that we send up to the fusion center, it keeps reducing the performance as well. And as we expect, the multi-sample sphericity test, of course, outperforms all of these because under the multi-sample sphericity test, we have all the statistics that we need to generate the test statistic for the decentralized sphericity test, because we are sending the trace and the determinants of each sample covariance matrices. That is all we need to regenerate the test statistic, the global test statistic. But under the meta-analysis, since they are only sending the p-values, some information is inevitably lost. So we can't expect the performance of the multi-sample sphericity test. So that is how each of these different techniques work. And yeah, with that, I think I will conclude my talk. So in this talk, my main intention was to give you an idea about this sphericity test, which is an interesting spectrum sensing technique, and tell you a little bit about some analysis that we did, and also share with you these decentralized approaches, the multi-sample sphericity test, and the meta-analysis based sphericity test. And if you're further interested in reading, here are some papers that we published based on these results, and there are also very nice references in these papers that you might be interested in. Okay, so thank you for listening, and if you have any questions, I'm happy to answer.
Thanks, Regita. So if there are any questions so we do the regular thing, either type it in the chat or raise your hands or just start talking. Okay, Ian, do you want to ask your question?
Hi, yeah, okay, firstly, thanks for a great talk. It was very clear, and being from a kind of nonlinear control background, I learned a lot about an area I've really had no prior knowledge of. So what I'm going to ask is more about connecting your area with my area, I guess. In problems like fault detection for control systems, a common approach is to have, let's say, a bank of multiple Kalman filters, and then you look at the innovations process, so the error between the state estimate or the estimate of the output and what your sensors are telling you, and check whether that looks like an IID process, which I think is basically, basically it's got a multiple of the identity for its covariance matrix. So I was thinking that in that context, you're kind of maybe looking at a similar thing where you're trying to test whether a particular process is basically IID or not, and whether you've seen this kind of sphericity tests applied in other contexts like that.
Yeah, so I was just thinking, I mean, as long as, because what we are basically checking is whether that actually changes the structure like that, like in my case, where we have that population covariance matrix that has that diagonal structure, and as soon as it departs from that diagonal structure, we can actually check that by using this sphericity test. And I think as long as that is applied, it is not very clear to me what your context is like, whether it is directly applicable or not. But as long as if you can write the generalized likelihood ratio, for example, for your case, and then if you can sort of maximize those likelihoods, because you can definitely write the hypothesis testing for that case, right? For your case, you can definitely write the hypothesis testing in terms of a population covariance matrix. But
possibly would apply. I mean, maybe somebody else in the audience knows more about the connection. But basically, if the system you're monitoring really does fit your assumptions, then what's called the innovation process of the Kalman filter will be white noise, basically. So if you look at correlations between
so they're all then independent elements in that matrix, basically. So that will give you a diagonal matrix for the population covariance matrix.
Yeah, but if something has changed in the system, you'll get all sorts of cross correlations showing up. So
then again, then you will have a sample covariance matrix that has a correlated complex Wishart distribution.
Right.
Is that right? Then it should directly be applicable, I assume.
Yeah, it's interesting. Yeah. Okay, thank you.
Yeah, I think, Ian, it really becomes, if things are correlated in time, it means there was a fault that is propagating through the network, through the system, right? So it's really the question of...
If it's correlated in time, it means that the actual system no longer satisfies the assumptions.
The assumptions, exactly. So it's not block diagonal, the structure of the... So I think it is applicable. I think because the test really determines if something is spherical or not.
Yeah.
Right. So if you have these off diagonal elements, then it's not. So I think it's interesting. I mean, it's a good observation. Yeah.
Good work. Yeah.
Yep. Thanks. Thas, you had a question. Regina, do you want to read the comment? And there is a chat.
Actually, how can?
Oh no! For some reason, again, it can only be sent to me. So I will read Thas's question. Sure. What is the target minimum false alarm probability? And in any practical design of any fusion center, I would presume there are a lot of messaging to get the system working. So exchanging few real numbers is. So exchanging few real numbers. Is it a scalability issue in terms of large numbers of radios sending messages? It appears for, hang on, I can do something.
Shall I answer the first question first?
No, hang on, I'm going to send it to you.
Sure. So for the first question, it was about the false alarm probability values, right?
Rajita, this is Tas here. I was just asking, what is the minimum false alarm probability that we should be aiming for? The question is, I was looking at your summary curve and then looking at, let's say, we're targeting 5% as the target false alarm probability, but you're the best method is able to give us maybe around anything close to 80% or so, I'm right. But you were trying to compress down the messaging from different radios to the fusion center. I guess that's what you summarized 4 different approaches. So yes. I was kind of questioning why that we need to really reduce the messages if the accuracy of detection is going to fall down. Is it a scalability issue in terms of number of radios sending too many messages, or is there any other complications?
Yeah, I mean, it is, yeah, one thing is, of course, the scalability issue, because like for the centralized approach, I do mean under the decentralized case, why do you want to further reduce from just 2 real numbers to 1 bit?
Yeah.
Well, yeah, I mean, it is, okay, I understand going from centralized to this one, we save a lot of information, or we save a lot of network overhead, because we are actually not sending raw data anymore. We are sending just 2 real numbers. But to even half that, again, that is to actually save the amount of information that we send to, let's say the fusion center is, let's say that is 1 cognitive radio that we use as the fusion center. The amount of information that we send to that fusion that cognitive radio is what we want to save, because we, in a way, we are actually also decentralizing the processing power by doing this, because we are doing some processing locally at the central processors, and also the amount of processing that we do at this global cognitive radio is further reduced when we go further down in this from one method to the other. So basically, to save the network overhead even further and to save the processing power is what the motivation was, to go even further down.
Thank you.
But actually, the main jump was, I agree, going from centralized to the first multi-sample sphericity test. That is when we did the most saving, but then we wanted to check other methods. Like, for example, in this case, by going from multi-sample sphericity test to meta-analysis, by halving the network overhead, we are not losing much in terms of the performance, for example.
And is there any difference between the central scheme versus decentralization? If we can put the central scheme on top of the same curve, how best that would be compared to the?
Yeah, actually, that is right. So actually, I should have included that too. So that, of course, has much better performance than the multi-sample sphericity test. Unfortunately, yeah, I didn't include a plot here. Sorry. Yeah.
Igor, go ahead, ask.
Yes, if you allow me, just Rajat, might I ask you to move to the slide where you define your test statistic?
You mean for the centralized?
It is one of the first slides, actually.
Oh, yes.
Just where you define it. Yes. In terms of as the ratio of the determinant of R divided by the kth power of the, okay, just let me, we'll make a few. No.
Just one?
Well, yes, I understand that you arrive at that quantity through, by considering the likelihood, the ratio of likelihoods, okay,
yes.
And the maximization of those likelihoods in the numerator and the denominator correspond to those different hypotheses. But if you now move to so the resulting test statistic is, of course, a quantity, is a non-negative quantity which does not exceed 1. It just follows from the arithmetic geometric inequality. And I also understand that R is actually a random matrix, because this is the sample covariance matrix as far as it stands, right? Okay, yes. But just a quick remark. So if we forget for the moment that R is a random matrix, but rather consider it to be just the covariance matrix of, say, a Gaussian distribution with zero mean, then if you take the logarithm of that ratio, with the negative sign and multiply it by, say, 1/2, okay, then you will get the so-called anisotropy functional, which was introduced in my works in the 90s and early 2000s. Okay, so the idea is the following. So if you consider an arbitrary, well, absolutely continuous probability distribution and compute its minimum relative entropy or Kullback-Leibler informational divergence with respect to isotropic Gaussian distributions, all possible isotropic Gaussian distributions, then in the case when the starting probability distribution is zero mean Gaussian with the covariance matrix R, you will exactly get -½ times the logarithm of this ratio, the determinant of R divided by the kth power of that trace divided by k.
Yeah.
So, and from the very name anisotropy, it is and from that different definition, it is clear that it's a non-negative quantity which quantifies the deviation from the class of isotropic Gaussian distributions, which well, since they are isotropic, they are ideally spheric. So this is a relation with your sphericity test.
Okay. Yeah, it is a nice observation. Actually, I would like to have a look at the papers that you've mentioned.
Okay.
Yeah, I kind of get the idea that you said.
Okay,
and thank you for that comment.
Rajita, there is a question for you in the messages, if you want to check it out. I was talking to myself, it was mute, so here we go.
Oh, sorry.
It was by Emilian, so he can clarify if needed, but the question is there.
Do you have any form of signals you can detect with? Okay, the question is, do you have any idea of the form of signals you can detect with the centralized version and not with the decentralized version?
So I think another way of asking the question is how much information do you lose by moving from the centralized problem to the decentralized
problem? Yeah, I mean, but I don't think there is like any particular form of signals that you cannot detect just because you will of course lose some information depending on what decentralized approach that you use, but I don't think there's any form of signals that you can't detect that you can detect in the centralized version that you can't detect just because you're sending limited information up to the fusion center. Like for example, one thing I can say is like I don't think that there is any form of signal that you can't detect. If you can detect it from the centralized version, it could be numbers, but you should be able to still detect it from the decentralized version.
Okay, maybe Emilian can follow up the question, because I think there might be something interesting there, but we are coming to the end of our discussions today. Thanks again for the talk, Rajita, and thanks everyone for attending. We're going to have another talk next week. Thank you.
Thank you very much, everyone.